Okay, let's start. Last time we started with Y connection, star connection for the sources, and when you try to find line-to-line voltage, line-to-line current, in star connection it's the same, in delta will be different, and I'll explain in a while how can we distinguish between both cases. Last time we explained star connection for the sources, and we found out that the relationship between the line-to-line voltage and the phase, as you see in the green box, the line voltage magnitude is equal square root of 3 times the phase voltage, and shifted by 30 degrees, leading. The line is leading by 3 degrees. And then the rest will be like minus 120. What about the current? The current will be the same in star connection. Line current equal phase current, magnitude and angle, no change. Because if you look here at this star connected load, you will see A, B, C, and we use the uppercase letter for the load and lowercase for the source. So you'll observe that the current IA go to the phase, IB go to the phase, so they are the same, no change. That's why we write here that the phase currents equal line currents. Let's take one example here. We need to solve this problem. It's a star connected load, and the impedance of each phase is equal to 20 ohm and the angle negative 30. When you have the all impedances are equal, we call this balanced load. And that's what we're going to study this semester, balanced load. What is the question here? They said that the line-to-line voltage is 120 voltage, and the impedance is given, and they ask for the line currents. You want to calculate the line currents, IA, IB, IC. So when you have something like that, it's easy to use something called one line diagram or equivalent line diagram, or equivalent one phase. You don't have to work the whole problem using the all three phases. Why? Because they are balanced, they are equal, and the only difference is the angle. So just try to find one equivalent phase and solve the problem, and then you can find the rest of the currents IB and IC. Means we are going to find only one phase IA. How we do that? We said we're going to use equivalent line diagram. Let's just cut this thing and okay. So that's the example we need to solve. So what we'll do, we'll try to find the equivalent phase. So we'll have sketch only one phase. So we'll have one impedance, and it's equal to 20 angle negative 30 ohm. Transmission line means there is no impedance in the middle. In the practice, I put impedance here. You can practice this. It'll be the same. You just add it to the load impedance, and you have a voltage. You're taking one phase on. Let's say you're taking phase A. But the voltage given here, 120 volt line to line. And you are working with one equivalent phase. What's supposed to do? you should get the voltage of one phase. What is the relationship between line voltage and phase voltage in star connection? The line voltage is equal square root of 3 times the phase. So now we want the phase because the line given. So we'll say that line to line, it was giving like equal 120 voltage. I don't care about the angle now. Just want to find the magnitude because I'll assume the angle. So the phase voltage will be equal to 120 divided by root 3. That will give us 69.28 voltage. Set the angle. If you assume that the line voltage on angle 0, and that's always the case, the first line to line will be in angle 0, then negative 120, negative 240, and so on. So you should know the relationship between line voltage and phase voltage for the angle. I just mentioned 1 minute ago that the line voltage is leading the phase voltage by 30 degrees, right? So if the line voltage in angle 0, so what do you think the first phase? What will be the angle? Negative 30. Why? Because the line voltage leading by 30, it means that the phase is lagging. So since lagging will be negative 30. And why I'm saying negative 30? Because we assume that the line voltage given in this problem on angle 0. Why am I assuming it's equal 0? Because it was not mentioned the angle value. So it's your right to pick it 0. So you will have the phase voltage on angle negative 30. That's the one phase. Yes.
120, how did you get it?
It's given.
Oh.
Yeah. So you will say that's the voltage AN. Why I'm saying AN? Because you're taking one phase and that's your N here, the neutral, connecting the all end parts of the source. And that's equal to 69.8 an angle negative 30 voltage. And you got the impedance and you need to find the current, IA. IA is the phase current, that's true, but I don't worry about it because it's the same line current. So the phase current IA as a phasor is equal the voltage AN, and it's a phasor, divided by Z. That will be 69.8 angle negative 30 divided by 20 on angle negative 30. So you get the first current. That will be the first current. It's equal 3.464 and the angle will be 0. And how can you find the current IB and IC and ID? First of all, this is phase current. I just did for one phase. In front of us, we call it one line diagram, or equivalent one line diagram, or equivalent phase. So that was a phase current. But because we are working with the line current is equal to the phase current. So this is line current also. So that's one of the question, that the line current in phase A. What about the line current in phase B? You do not have to solve it or solve it. No, just you find the relationship between IB and IC and IA. What's the relationship between IB and IA when you have balanced three-phase voltage? Angle, yes. What is the value of the angle, Chef? Between IB and IA? 120. So I should add 120 or subtract 120? Subtract 120, that's right. So you have 3.464 and 0 minus 120 would be minus 120 degree M. IC. Can subtract another 120 from IB. So if you do that, 3, 4, 6, 4, angle negative 240 degree. And if you like to have a positive value, you can add always 360 to any angle. It doesn't change the value. Just instead of looking from this side, the other side. So you have 3.464, and the angle, if you add 360, you got 120. Yeah. So that was easy when you have. Yes.
Quick question. So
Yeah. Because that's the phase voltage, and the line voltage, assume it in angle 0, and in star connection, the line voltage leading the phase voltage by 30 degree, it means that the phase voltage is lagging the line current by 30 degrees, so I put it negative. Yes.
If we're finding the phase voltage by impedance.
Because in star connection, the line current equal phase current. If it was delta, it will be different. It will be that the phase, and they have to find the conversion. Yes.
The phase current always equal to line current?
In star connection only. Yes, not in delta. Well, so it looks like you guys excited about delta. All right. Let's see the delta. This is delta, but this is load. Let's see first what happens if you have source connected in delta. We'll go to the load. Because the other. As we learned before, when you do source, that's the source, make it like that. But this time it's connected in delta. Single phase circuit in the lab, then you will start with the 3-phase. Will be done with the chapter. So that's the delta connection. Let's take, we use small letter or lowercase a, b. So that's the phase. So you can say that the phase VAB, V. Positive, negative, positive, negative, positive, negative, and just like that. If you take this direction, A, B, B, C, C, A. And the current, you can say that the current now is coming out of the source. So that's I, A. And coming out of C, that's IC, IB. About the line-to-line voltage, obviously, this will be the voltage between A and C. CA. And it depends what you're looking for. If you want to keep it the same, so I'll say, okay, I will look at the voltage VC with respect to A. And between the other two lines here, you have line C, you have line B. That voltage between C. And the last one between A and B. From delta connection, what do you observe about line voltage and phase voltage? They are equal. If you look between A, C, for example, between A and C, the phase, that's phase AC, and the same, it's the line between A and C, the same. So in delta connection, voltage, line to line voltage is equal to phase voltage. Y star than the Y or star connection. But the current is different. If you look at IA coming out of the generator here, at this junction, what the current yet? From A to B, that will be current IAB. From B to C, IBC. And from C to A, you will have the current ICA. So the line current, let me just get one current. The line current IA, for example, that's equal to what? If you apply Kirchhoff current law, you can say that this junction, the input is ICA, and the output is IA and IAB. That's Kirchhoff current law. If you want to find IA, so you will say IA is equal to ICA minus IAB. Sure? So IA equal I. What is the relationship between the line and current? First, the phase current in the sequence ABC will have IAB, IBC, ICA. They are shifted by 120 degrees. So let's just do that. You have IAB, that's the first phase. The second phase, IBC. The third, ICA. These are the three currents in the phase, ABC, sequence ABC. I want to find IA, so just I will check the relationship between IA is equal ICA minus AB. CA, that's CA minus AB. To make minus AB, all what I'm supposed to do, just flip. That's minus the AB. And I add it to CA. So if I add it to CA, I'll make a parallelogram like that. And that will be the resultant, which will be IA. That's IA. And as you know, we did that before. That's third degree, that third degree. That before, it's just the same. So now you want to find the relationship between line current and phase current. That's line current. And that's phase current. So there is angle difference and there is magnitude. The magnitude obviously is like the same way. If we did the same method, you will find the magnitude of IA is bigger than the phase by square root of 3. Have the same angle and everything. So line current is bigger than phase current by square root of 3. What about the angle? If you look at this angle, you can say that IA is leading IEB by all this angle. What is this angle? 30 degree plus 120 here, because they are 120 between IAB and ICA. So 120 and 30 will be 150. So now we can write IA is equal square root IAB magnitude and the angle, if this angle 0. So you have 0 plus 150, 150 degree. So line current is square root of 3 bigger than the phase current and leading by 150 degree. Means you're adding, you're not subtracting. Of course, you can find the rest of the current. IB will be root 3. And you can write any current, BC. What is the angle different here? Actually, all the magnitude are the same, so you don't try to have to write to The magnitude of IAB, IBC, all the same I. We call it I. So let's just call it I. That's the root mean square of phase. So IB will be behind IA by 120. So you subtract 120, you get 30 degrees. In any balanced three phase, delta or Y, always any line on any phase shifted by 120 degrees, behind by 120 degrees. So we have IC will be square root of 3I, and then you subtract 120 from the 30, you get minus 90. Force, not load. When we are dealing with the load, it will be different. I'm not going to make the proof. It's very similar, but the sequence will be different. And I'll tell you why it's different. But do you understand how we got the relationship between magnitude? Line current is bigger than phase current by square root of 3, leading phase current by 150. That's the source. What about the load? The picture for the load. Yeah. I will use all the same sequence. We're going to use A, B, C, the same thing. So you have here A, C. The difference is this is load, so not producing current, taking current. So that will be IA. IB, I'm sorry, I'm C, IB. The voltage will be the same. The phase and line voltages are equal, doesn't matter. Delta connection, load, or source. The same sequence of current. Of course, we'll assume that Z impedance are equal. So you have the current here, IAB, IBC, the same as we did in source. But what's the difference? The difference between load and source, that the current is in. So it will change the equation. The in, now we have ICA and IA, they are in, and the out is IAB. You want to find IA. So IA will be equal to IAB minus ICA. IAB minus ICA. Last time was ICA minus AB, right? So I will just sketch the phasor diagram for the phase current IAB, IBC, ICA. This time IA is equal to IAB minus ICA. Flip ICA, and then I complete the parallelogram. That will give me the result, the resultant, which IA. Yes, the magnitude is still bigger, I know that. So I will have IA is equal to root 3 times I, where this is the magnitude of the phase current. The angle is different. It's below IAB by 30 degrees. So you say, if this is an angle 0, so that will be minus 30. And then you can continue and write the rest of it. The rest will be easy. Minus 20, minus 150. And subtract minus 120, we'll add 120. 90. So as you see, the load connected in delta way, you will find the same relationship for the voltage, just true, but it's different than the source. In this time is lagging by negative 30. When it's source, it's leading by 150. When you go to the lab, how you connect the star and delta? If you have load, you will have like resistor or inductor, whatever. That's why I'll make it look like a box, because you have three types of load in the lab. You got resistive, inductive, and capacitive. In any one of them, I'll just represent them as a box. We have three of them. How you connect it in parallel? Let's make the yes. Because you subtract 120 from each line. Like you see, that's negative 30. How you get negative 150? I subtract 120 because it's balanced three phase. How you get this? Subtract 120, but to make it positive, I add 362. Yes.
The angles and this.
Which example? I did only one example, the star connection. I didn't do the delta. Or you mean the source?
Yeah, because if you go, that's like different.
Are you talking about that? Yes, that's what I'm trying to say. What I'm trying to say that the angle of the load will be different than the source, because when the current IA in the source coming out, so IA is equal ICA minus AB. Remember that. But when you go for the load, the current is in, so IA is equal IAB minus ICA.
Okay.
So it's flipped. Yeah.
Okay.
Any question? So when you go to the lab, you have three loads for each phase. How you connect the star? How you connect the delta? Let me make the same. I will do that in the top one as a star. It's very simple. All what's supposed to do, a beginning and end. If you say that is A, that's A dash, B, B dash, C, C dash. And that's even when you go to industry, you will find they have motors and they have the terminals exactly like that. They have switch here, then you got to connect it in star. You just connect this one by this one, and then you just make short circuit on the end of the three. You got a star. So this is why connect. And these are the terminals that you, if you want to supply current, you connect it to the source. Because you have a three-phase source. Then you connect this to the source. Because most of the motors and generators in industry, three-phase. All big motors, three-phase. And the input will go there, to the ABC. How you connect delta? You have A dash, B, B dash, C, C dash. You connect the beginning of one block to the end of the second one, like that. That's A connected to B dash. C dash. C, you connect to the other one, so C, A dash. And these are the terminal that where you put the supply. That will be that. If you rearrange it, you'll find it's equal. They make it nice, but this is how you do that. So why I'm saying that, because when you go to the lab, after 1 week, you do the connection. So that's the way that you're going to make the connection for delta. Star is easy, but delta usually is confusing. Okay. Let's take one example in delta. But before I do the example in delta, there is something. It was nice and easy when we have the star connected load and we take only one phase and we work on one phase. It's always easy. I don't know if you have circuit 2, if you work with 3 phase, it's a hassle when you work with every single phase. It's just like you have like 2 circuits working at the same time. But making that, and we don't have to go back and do this difficult way, because always we're going to use balanced load. All impedances are equal, all voltage magnitudes are equal, shifted by 120. So I would like to use one equivalent phase. But what about delta? You cannot just take delta and you will say, I'm going to take this phase. It was easy for Y, because we have here the phase are separated, but the neutral. You don't have neutral for delta. You cannot take it. And there is a way, but it's hard way. You're going to have like solving 2, 3 circuits. But there is a way. Do you have idea what's the way to make it easy and simple like the star connected load? The circuit, like, let me just give you an example. If I take the same problem here and I ask you, okay, just solve it and get the current in every line. Let's load, and I'm going to connect it to source. And find the current, line current. And the impedance are given. Let me just give you a numerical example. So how to make an easy way like what we did. Let's say the impedance is equal 5 on angle, -30 ohm. Say the voltage is the same as we did last time. It's the line to line voltage, 120 volts. I'm just going to give you a hint, and then you can do it at home. This is the line voltage, 120. How you solve this? And you have delta? Yes. Delta. So the best way to do it, convert it to Y. So you can have the neutral. If you do it in, if you convert in Y, it will be something like that. The equivalent Y. What? Oh, it makes big difference. If you have it connected to Y, so that will be like, if this is A, B, that will be the neutral. So you can take only this phase. Let me sketch it nicely now. The equivalent star. And I'm still keeping the terminal A, B, C, they don't change. I just change what's inside. Just nicely. That's the equivalent Y, and I have the points A, B, and these are the lines. We have 2 questions. First question, what is the value of the impedance? Because obviously it's not the same. Delta is 5/30. It's 5/30. Yeah, just assume 5/30. So it's impossible you can say this 5/30. Not the same. So what you're supposed to do in circuit 2, you learn how to convert from delta to star, from star to delta, right? I'm not going to go through the hustle, but because we have a nice system, balance, doesn't balance, all three impedances are equal. When you want to convert it to Y, just divide it by 3. So to make it easy, so let's change its example. Give a nice number. I will say 6 over 30 degrees. Just when you divide it by 3 will be easy. So if you divide by 3, so the equivalent ZY will be equal 6 on angle 30 divided by 3, you'll get 2 angle 30 ohm. That's the first step. Second step, you are going to take equivalent one phase. So you have to find the value of the phase voltage. It was given 120 voltage for line to line. As we did last example, what we did, we said that if you have the line voltage is equal 120, and we're going to make it 0, and then we to find the phase, the magnitude will be what? 120 divided by 3. Why? I'm trying to find that. And then, what about the angle? As we did exactly last time. That's line to line 0, and then the phase will be like shifted by 30, negative 30, right? Yes, negative 30. So about negative 30. And then you solve, you find the current. It's easy, of course, now to find the current, but you are finding the current here. Find the current in this phase, right? It will be the same. So IA is the voltage of the phase, that's the phase AN divided by Z, Y, that's 120 over root 3. I think we found the value of 1. I don't remember. 69, okay, good memory. 69.8 and angle negative 30 divided by Z is equal to an angle 30. Just, I mean, I will change it, make it negative 30, just to make life easy. Negative 30. So it would cancel. We'll have it easy number. So 0.8 by 2, 34.9 angle 0. And that's IA. Can you find IBIC? Yes, you can. IB 20 and IC will be 34.9 angle 120 plus. That's IA, IB, IC. Question is determine line currents and phase currents. The load was not going to start. Why did that? I just did that to make it easy for me to solve it. So I found the line current. So I have to go back to the delta and I put the value that I got. I got IA, I got 34.9. Angle 0. That's IA. That's IC because that's C, that's A, that's C, that's B. I got IB the same, will be equal to 34.9 angle negative 120. IC equal 34.9 angle plus 120. And the question now, I want to find the phase. It's enough to find one phase. Let me look for IA because we did that before. We know the sequence is just going in this direction. So this current will be IAB. And if you remember, that will be IBC and that's ICA. Now, You have to find the relationship. You can do it again or just use the result that we did. What we did before in load, we found the relationship between line current and phase current, right? What was the relationship that we deduced? The relationship between line current and phase current. Line current is bigger than phase current in delta by square root of 3 and lagging the phase current. If the line current lagging phase current, so what the phase current? Leading by 30, right? So I will say back here. I want to find IAB. IAB is the phase current. Smaller than line current by square root of 3. So I will say IAB equal the magnitude of the line 34.9 divided by square root of 3. And the angle is lagging or leading? The phase. Let me just go back again. I have a short minute. I have to make sure that I get it right. Oh, here you go. That's the line current. That's the phase. So the line current lagging, so this will be leading. So I add 30, leading. All right. So I go and I will add 0. I add to the 0 30 degrees. And that will be the first phase current. 34.9 over square root of 3. Let me just calculate. Got 20.1. Say 20. So it's almost 20. Angle 30. And that's IEB, the phase current in delta. So the rest of it, let me write here the answer. IAB, IBC, ICA. That's 20. Angle 30. That's 20. Subtract negative 120 and negative 9. That's 20. You can add 120. Sorry, half. Negative 9. Negative 120. If you make it negative, negative 210. If you subtract 120. If you want to make it positive, you add 360. We have 20, 60. That would be 150. Both are right. Okay. So that's how we calculate it in delta connection. So we took advantage of the star connection to use only one diagram, one phase. Yes. Oh, I get 150?
Negative 90.
Negative 90. I say 30 because you see that's IAB. Then behind IAB by 120 degree, IBC, and then ICA. So IBC is behind IAB by 120. So I say 30 minus 120 will give me minus 90. Any question? Yes.
How did you get 20?
I divided the line magnitude by square root of 3. That's, here you go, in this step, 34.9 divided by square root of 3. Any question? You understand the delta connection source? I will upload I think I uploaded already. So make sure that you understand it, and because maybe I'll give you quiz online after you study the subject. I'll give you like a couple of days. So maybe Monday I'll give you a quiz online. At the time of the lecture, and we'll continue where what's left in the three-phase system. That's just the basic. I know you got it in circuit 2, but I want to make sure you understand. I want to make sure. So next time I'm going to show you something that you're going to use in the lab, how to measure the power in three-phase system using 3 watt meters and 2 watt meters. The most famous one, 2 watt meters, and I have lab already. I prepared the lab manual for you for using 2 watt meter. This is what's used in industry, 2 watt meter method. And then we'll explain how to use the capacitor to improve the power factor for load that it's lagging and has a poor power factor. And that will be done with three-phase. So I think maybe it will take next week and we'll be done with it. Then we'll move to the magnetic circuit, we'll go to the machine and transfer. Any question? Right. I just like to remind you, please try to practice before the quiz come in or the test.